Hello, my name is Anton. I'm from Chain Security. Yes, we are started in 2017 and keep going, as like Chiba told. And yeah, we are quite long in the game, so to say, and team rotation is surprisingly low, so we are almost all the same people, keep doing audits and securing the Ethereum. I mean, we are, I think, at this moment still somewhere 5th place on the Ethereum Foundation bug bounty leaderboard, and yeah, we are trying to secure whoever comes to us for advice, and also like trying to find bugs in our, like, so to say, free time. Yeah, maybe some people know about read-only reentrances. This was kind of discovered by one engineer of ours, and yes, I mean, as the previous speaker told, like, it's really hard to navigate this field in terms, right? And here I want you to tell about this kind of mental model. Like, we are sort of, we're initially a spin-off of ETH Zurich University. Its name is funny looking, but it means like something like Federal University of Switzerland. But basically, one of the things that I believe like developers and auditors, no matter what you do, I mean, I think anybody who is more or less involved with code can profit a lot, is this kind of mental models, how to deal with complexity, how to deal with code that is hard to reason about. And one of them is like invariants. So, I mean, in a nutshell, like what you see is like a definition of invariant. It's just some property of a, in our case, program, but it's a smart contract that is always true, right? So, one of the such kind of really intuitive properties that you might maybe see first time is that maybe total supply of ERC20 token, if you have experience with ERC20 tokens, is equal to sum of balances, right? This is kind of makes sense to do because you don't want to have like tokens in balances but not accounted in total supply, right? So here I'm going to use a bit more complex example, like it's compound V2, I think, actually. It's, let's say, not so popular nowadays. I really don't know how they're doing, but like we started long ago, and when honestly we started in 2017, most of the audits, most of the contracts we reviewed, this was like ERC20s. Like, was peak complexity in most places. And then like with time, like when people thought about this composability of tokens, it started to think how we can create systems that utilize this underlying simple primitives like ERC20 tokens, what we can do with them. And yes, exactly, compound is a thing that you can do with primitive ERC20 tokens. It's basically lending and borrowing platform. So you have here DAI. This is like a stablecoin. I'm going to use this as an example of that's kind of a token that Compound will be using. And then CDAI is basically a token that Compound creates internally when you are lending the DAI to Compound, right? I'm gonna show later why they're doing so, like, but so to say, you can say that DAI is some external token, and CDAI is a token native to Compound itself. And of course, like, there's gonna be Ether, it's a native token, and yeah, you're as well gonna see why we use it. Okay, now like once we saw like these 3 basic blocks, let's first go into the first part of our like Compound dive in, right? And I'm gonna just explain the system, and then like after I explain like first steps, I'm gonna try to show you how you can kind of abstract the complexity out of this quite a complex behavior with quite small and simple formulas that's easy to understand. Okay, first it's in Compound. I told you it's lending and borrowing platform. What is lending? Lending, it's you can say a process, right? When a party, some lender, it could be you with your Ledger wallet or MetaMask, whatever you're using, you have some DAI tokens lying around, and you basically want to give them to get the yields, right? I mean, if you know what yield is, this is exactly why people are lending. They either putting it into some liquidity pools or something to make the kind of capital work, right? And like you see, it's usually if you put them inside, so this is we're gonna call like supply, this kind of step. If you're supplying tokens, in exchange you're getting CDAI, right? This is like a virtual token, so to say, that represents your like position inside this compound system, right? And after a while, time goes, and you actually want to get your gains from the compound, right? You say, yes, I'm done with farming compound, like I actually need DAI, because DAI you can use for many other things, like withdrawing from exchanges, centralized ones, and actually like buying pizza, what to so not. And this time, how compound works, why you actually incentivized to give your tokens to compound is because you'll get more, right? You see here you'll get like 105 tokens and not the initial 100 that you have to put. Like, so with time, like when you will be withdrawing, this is process we call it, you will get more. And this is, I would say, one of the simplest invariants that you can kind of check when you are doing audits or as a developer when you're writing a code, right? And like a bit more complex example, but in the same nature of invariant is that price of DAI to CDAI with time should be monotonically increasing, right? So there should not be moments like when CDAI is not, like let's say I put 100 DAI and I got back 40 CDAI. There should not be a withdrawal where I'm actually getting less DAI, right? I mean, this is compound invariant. It's not doesn't hold for all kind of protocols you're going to deal with. I mean, even for example, I know Certor who works with Auer. In their case, there is some potential like rebasing that actually permits this balance to go down, but in general, as a general rule, like this shouldn't happen in most lending borrowing platforms, and this like exchange rate of you can say DAI to CDAI, like or any other token to like internal share that represents this token should always go up. Yes. Now we're gonna go on the other side of this compound is borrowing. Borrowers are exactly the parties who want to get like the collaterals that you the tokens that you have deposited, and they are expected to return more for like ability to use your tokens, right? In this case, we basically cannot use DAI again, like to to borrow from compound. We need to use another type of collateral. In this case, we're going to choose like a native Ether, right? And as example here, borrower can supply collateral as Ether, as I told, and back he can get DAI, like a token that I told you is more usable than maybe for his needs the Ether, right? And his Ether is not burned. It's not. He didn't lose his Ether when he deposited the borrower. He actually later can repay with some extra fee, right? Extra percent on top, and get his collateral back, right? So this is like a repay. In this case, you can see like we are returning a bit more DAI, right? And this basically, just to spoiler you, like, and people who know this, it's like quite obvious, profits of lenders come from borrowers, right? This like system itself doesn't print new DAI, right? It's only can kind of redistribute what lenders or what borrowers kind of have to put on top, right? And invariant for this is quite simple as well. It's a repaid amount. It should be more than borrowed amount, right? So you want to borrowers to pay for ability to use your DAI, right? Other type of collateral that lenders had put into the system. Yeah, and like if you just paraphrase this, what we wrote here, like this is actually the same exact equation, but we just are adding extra components there because there exists actually certain term like prices, right? You don't want to give 100 Ether if Ether only costs 50 DAI if you use some other exchange, right? It will be really bad deal for a compound as a protocol, right? You don't want to kind of distribute assets without like proper backing. So that's, you want to be sure that borrower at least puts enough funds for like incentive to repay, right? And the result, like the previous repay amount more the borrower amount, basically results that like collateral multiplied by price should be more than your borrowing, right? This is like invariant for like repayment. And actually, like, yeah, I touched a bit, that's like repay, you should be incentivized to repay, and exactly what happens if, let's say, we have at this moment, I don't know, it's like, I have not introduced full variables, so people who know maybe say that's not a possible situation. Like DAI is usually one-to-one with US dollar, right? And for, let's say, 1 Ether, I can get 100 DAI, right? This metaphor situation. And exactly if price becomes, for whatever reason, 50, right, it's much less than actually the amount of DAI currently borrower owns. Borrower has no incentive to repay. So he will be actually not repaying, right? And this is like not good for protocol, right? Because as we saw previously, we want lenders to be sure that their money are working, they are like accumulating fees and so on. We don't want them to be like not happy and lose their tokens, right? That's why basically there exists another party called liquidators, and liquidators are like a party that can repay a debt at like assuming like prices they are like developing with some like how it's called, as a function over time, right? You at some moment know that like the borrower doesn't have enough like enough collateral to repay the debt, right? And this moment, like in compound, something starts, some process starts that is called like liquidation auction, and it allows liquidators to like basically liquidate the borrower's position by repaying DAI. You see, like he needs to return what borrower has borrowed at some like smaller price, and as a return he gets a collateral that potentially can worth more, right? Like invariant that you want to establish in this case is like to make sure that liquidator is has all the incentive to like liquidate position, is that basically the like I can read formula, it's quite big. Collateral amount multiplied by price of collateral multiplied by collateralization ratio, I'm gonna tell us a bit later, is more than borrowed amount times price. So in our case, collateralization ratio, it's the factor that resulted in borrower's amount here not to be 100 but to be 80. Why it's 80 is because you exactly want to have a safe gap like in time in which liquidator can come and liquidate your position. And for that exact reason, for 100 USD tokens, you're not getting 100 back. This examples that we had before, they're technically like no protocol works like that, I think. It's collateralization ratio of 1 is a thing, but it's quite a rare thing. In most cases, you will get something like 0.8 in this case, which basically means that borrower cannot fully utilize value of his collateral. He can only do it partially. But as a result, protocol gets sort of like a guarantee. You can say that if price of collateral drops below the kind of collateralization ratio times price of collateral times the amount of collateral, then basically third parties like liquidators can come and repay the debt. They are really motivated to do so because they actually, you can see, getting like Ether is 99, right? But wait, I think I have a typo there because they should only repay 80 DAI and not 99. Yeah, sorry about that. Because you're not paying full price. You can actually like pay only what the borrower owes. Yes, and like price fees can be different. There is an on-chain, off-chain, but more or less it's always like some function over time, and this is great security considerations needs to be put into what exact price each protocol needs to put. But more or less, like you can say, the heuristics is such that you want to be able for liquidators to be fast enough to liquidate the positions. What if they don't liquidate? There is like bad debt as a term exists that exactly if like, for example, borrower has borrowed 99 DAI, but liquidator repaid only 9 DAI, right? This 9 DAI will be considered as like a bad debt. It's basically protocols usually have like a special pools to protect from bad debts, like they are basically funneling parts of their like protocol fees into the special pools that in case if they like accumulate bad debt, they can repay certain risks, right? But in general, they never want to have any bad debts on any of their borrowing or lending positions, right? And there is a huge effort put into like analyzing what exact collateralization ratios needs to be in each system. It's more not like security in like DeFi sense, but it's still security in DeFi sense, but it's more like economic parameters and not like software code that can be broken, right? Okay, and yes, for like desired invariance that we would like to hold is that collateralized amount multiplied by price of collateral. Price in this case you can say it's like in dollars, right? And multiplied by collateralization ratio should be borrowed amount times price. This is the old formula that you saw, and basically what it like really means is that like intuition behind it. It's kind of one of the things hard to get is you all see these formulas, and with time intuition starts to build up, and here intuition is that basically what borrower puts in should be less valuable than what he gets out, right? And yeah, this is, I think, enough for borrowing. We can now go for connecting both pieces of the puzzle together. It's lending and borrowing. So there's lenders who come and put DAI, there's borrowers who come and like get DAI and put another asset as a collateral, and later they repay, and their repayments go and basically result in profits of lenders, right? And yeah, this invariant, if you like sum up stuff on the left side, on the right side, on the left side, they should be equal, right? Because the inflow of a system, assuming there is no like protocol fees, it should be like net zero. And as you see, like borrowed supply plus borrowed repaid borrows should be equal to provided supply plus collected fees, right? So this is what I told you like in the very beginning, that value doesn't appear from nowhere, right? Compound doesn't mint Ether, compound doesn't mint DAI, and it's like basically a barrel where some people put their assets, some people take it, but barrel is full only because some people put it there, and barrel is not empty because people have not taken everything out, right? So this is how you can have like an intuition behind like what this formula means, right? Okay, why you need to know about all this invariance, and like what do they actually have to do with like writing code or like auditing code or many things? And this is exactly that you need to utilize these things for first testing. Second, like even if you just writing code or looking at code, you need to consider these things for each function, and it honestly speeds up a lot of the process. Like instead of looking like, okay, what's can happen bad to system, you just basically formalize this invariant, and just you go function by function and check like, does this function break invariant, or it's actually good and maintains it, right? And in this case, in many cases, like invariants are like something that you can test only if you do the top of the pyramid. It's like if you do like system-wide test. In rare cases, like you can do like invariant testing for and test like even unit testing. I think there was much of good talks like by Trilopits, who told like about this tests and that you need to go for not only for 100% statement coverage, but also to go for like meaningful tests that tests. And one thing of you can do meaningful is test invariance of your system. Yeah, there's also a bunch of other more fancy ways than like regular tests to test the invariance. One of the ways is what I'm personally like fond of is like property-based testing. Yeah, I showed some examples how that of libraries and like builder tools that can help you with like writing such tests. I mean, Python is Brownie, Foundry is like where you can write tests directly in Solidity. Truffle, it's a bit harder. There's like only fast check exists so far as I know. But nevertheless, like property-based tests are really good. I'm going to tell you later what exactly that is, but stateful testing is another variant of property-based testing, but where you like maintain a state. And formal verification and monitoring is kind of I say formal verification is super advanced kind of testing technique, but it gives you the most guarantees. And if you want to go the last mile and basically be sure that you're safe, it's maybe like exactly what as a protocol developer you want to do. Monitoring is like more, if something bad happens, you have a way to basically pull the like stop and like prevent system from being like abused, but it's not most likely the way you want to deal with the kind of problems in your system, because this is like a last resort kind of system. Okay, and regarding property-based testing, I kind of mentioned it, but actually I should have reordered slides. That's basically if you consider a unit test for like something like deposit function, usually you just run one value through it and you just see if it's like passes or fails. Maybe you have after deposit you're actually doing some like queries and like asking smart contract if the state is okay, right? If I want to deposit, I want to see that something total collateral in the system has increased, right? And this is basically your properties that you are testing. Property-based testing is pretty much the same, but you are like bombarding your like unit test with many random inputs, right? And you still checking all the same properties, but just not on one input, but on many different inputs. It's still like good, I think as not from Trilopits told, like to limit basically if you're using really big integer values or really small integer values, there is this basically corner cases that you want to capture, but in general this is like really good testing technique and yields, in my like experience, a lot of results surprisingly with little time invested, sort of. Especially like for us, audits are time bounded, and it's always trade-off between like testing the client's code and like looking at code ourselves. Yeah. I think I'm done. I don't know if I'm on time. Yeah, I guess questions if anybody has. I think there's a question.
Thank you for the talk. I was wondering about the property-based testing. How do you choose the corpus that is used for injecting?
Sorry, what do you choose?
The corpus, like on the next slide, you have like 110. And okay. I was wondering about the corpus and also the seeds that generate maybe the corpus.
Yes, okay. So this is like really depends on library. I mean, I can, for example, tell you about Brownie. That's basically you're writing tests like in Python, and there is a like well-established library in Python called like Hypothesis that basically allows you to annotate certain input argument of your test as a parameterized test with a certain strategy. The strategy, you can specify minimum value, maximum value, seed. That's exactly like where it can be specified. And then this test will be basically run multiple times. And it will be every time like a random value from these parameters of your strategy picked. Yeah, I mean, I guess it really depends on like libraries, right? I don't know what's Foundry honestly doing there. I can only like speak about Brown just because I looked really into internals. But more or less, I think there is a standard, the way of how things you are doing is the same. Like you basically have a special way to write in like testing library that certain test needs to receive random inputs. Yeah. I don't know if it answers.
Yes, I was wondering about how to optimize actually the good choice of corpuses.
Oh, this is like really, really good question. Okay, good. So like in my experience, it's like you know for a given function that this function somehow mutates the state, right? And this like mutations of states, they are usually, and you can end up in a bunch of new other states, but for example, if you have, let's say, in our case, whatever, like deposit function, you can have deposit that, let's say, makes your collateralization ratio healthy again, right? Or it makes your collateralization ratio unhealthy, like if you maybe like withdrawing, right? So you basically, in my experience, it's best to look a given function and see what can be possible results, right? And then maybe you even like can target the values such a way that you say, okay, please, I want to deposit exactly enough assets with some random parameterization around it, so my collateralization ratio becomes 1, right? Something like that. And then you kind of, you can say, trying to fuzz around edge cases, right? You most likely, from like system, know like edge cases, let's say like even transfer functions, like you know maybe critical parts is like when you're trying to transfer more assets than somebody has, right? Or you're trying to mint really, really big value, right? This is where usually problems can happen, right? And yeah, it's really like protocol specific. Yeah, I can like say from my experience, we had like really one hard property we had to fast, and there like exactly was, you could say, like Uniswap v3 kind of system, where you could, when you're swapping, you can swap and cross the tick, or you can swap and like not cross the tick, right? And then you were exactly trying to give all these values as a pool of arguments to get from, right? And we basically wrote a property that we're testing that, okay, if I'm crossing the tick, liquidity should drop. If I'm not crossing the tick, liquidity should stay the same, right? And this like basically helped us to kind of find some problems. Yeah.
Hi. On the previous slide where it said formal verification, how does that differ from the others, or is it like an umbrella term? Did you mean something more specific?
Oh, yes, I guess Certorum. Yeah, I mean, it's really like a wide term, but what it results is you are having usually like high-level specification of your programming system, right? It's maybe like, I want to create a token, and in token you can like mint and burn, right? This is like in plain English, I have a specification. And next step you do, you are formalizing this plain English specification into formulas. There's usually some like special languages how you can express your properties. Exactly like, for example, for tokens, you can, I think like Certor talk, like you can have this kind of rules that tell you if user A transfers 100, like X tokens to user B, balance of user A should be decreased by tokens, and balance of user B should be increased, right? So this kind of formalization happens. And then afterwards, there's like different ways how you can basically create a model of your contracts, right? It's basically, you can say, math formulas instead of the real real bytecode, right? And your formal verification basically checks that your specification together with code is something that makes sense, right? Because it's really like formal verification is the strongest of them all, because in all previous values and like here, we are still poking dots in our like state space of all possible input values that you can put into the deposits, right? It's like uint, it's 2 to the 256, right? It's like too much. You're never gonna have it like count to it if like university collapses and so on, right? Basically, formal verifications is kind of tool that allows you to kind of really know that your function depends good on all widths of your arguments, so to say, right? How it does it? Because they are using like symbols and formulas instead of the real values. Yes.
Thank you.
What are the difference between first testing and property testing?
Which testing? Stateful and property? Or?
Property-based testing and first testing, what are the difference?
Fast testing and property? It's actually almost the same. There is like, I think, like, there are many people who kind of, especially like in science, who are really, let's say, zealous about the terms. So fuzzing usually in their terms means like you are doing black box fuzzing, meaning that you don't have idea about internal representation, you don't have idea about internal properties. Property-based testing is basically fuzzing, but you have idea about what exactly system is built of. As I told you, like you have idea about possible transitions and you try to like basically guide your fuzzing into this edge cases, right? This is basically it. In most cases, people use them interchangeably. I think if you open like Foundry documentation, they basically have fast testing and then the next, but the HTML link has property-based testing, right? So it's kind of synonyms, I would say, in crypto community.
Thank you.
Thanks for the talk. Could you please discuss the applicability and acceptability of monitoring and also what exists in terms of tools for this?
Yeah, I mean, we had the experience with some monitoring. I think we like worked with Forte a bit and like tried to see how they works. I mean, the only problem with monitoring, in my opinion, is that hackers are really proficient about the ways how you can like deploy transactions, right? How you can execute code. In many cases, there's like MEV services that can be used to basically execute transaction such a way that you see it only if it's already happened, right? It's in most cases too late. But in some cases, if protocol especially designed with ways where, like, for example, you are limiting throughput of tokens from Optimism to mainnet, like, for example, Maker has it for their like teleporter contract. And then in this case, if you monitor like some properties that what amount of tokens has been moved, you may have like some like alerts to say you bad things happen. But in most cases, like people don't, in my experience, don't design systems where they have this pull the plug kind of safeguards, right? And as well, like it's in some cases, like you can see people, okay, we have monitoring tools, hack happened, and they say, okay, we detected the hack, right? But in the reality, it's like a bit too late. So yeah, it's really works only if you design your system around monitoring, right? If you really put a lot of like this, let's say, rate limiting things around, or you put this kind of circuit breakers, then like if you detect, you can circuit break, basically. This is my take on it.
Thank you.